welcome, 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 welcome. Let me just check everything is good. That's good. You can hear me fine. That was a little loud, sorry. All right. So, happy to wake you up a little bit because I'm still waking up with some coffee, which I ran out of, which I need more of, but we'll get to that. I wanted to go over because I had a session yesterday and I got a really good example with one of my students on how everyone solves things differently and how you should not be copying anyone else because it's a big self-report. It's a huge self-report. Everyone solves problems differently. And many times a teacher can look at what you solved and then what your neighbor solved. And then when you go away from how you normally solve a problem and all of a sudden you do something that wasn't expected, it's probably because you copied that. So I want to make that clear. Why everyone, every student can solve a problem differently and still get to the same answer. That's kind of the key here. Because it has to do a lot with just the general way we think in our own heads, how we differ from each other, how we're not all cookie cutter molds, and how we all need a unique set of understanding for the most optimum way of learning, right? We have to understand ourselves and how we learn, which there's a whole spew I got to go about at some point about visual learners, auditory learners, and kinesthetic learners. That will be a future video to kind of self-identify yourself because this is what I do on every single case session. I try to figure out what kind of student I am working with and then how I'm going to present the information so it's easier for them to understand me because I can do the same thing over and over and over with every single student and the same exact methods, the same exact steps, but there will be an issue. There will be an issue of does this student think like the other ones, which is 90% no, right? So, how do we solve math in any kind of different directions and yet still end up at the same final answer? It's almost like how do you paint a masterpiece? And you can paint it as many different ways as you can think of with different materials, with uh, oil painting, with regular paint, with countless material types, right? Different canvases, everything. But you can still make the same picture in the end. And that's really where this art form pops in. How do we get to the same answer with different processes? Well, it all comes down to PEMDAS, believe it or not. Some case scenarios, we're considering some steps can be done first, but in the end, if we do one thing first or the other thing second, we end up still doing the steps themselves, whether a little bit delayed, which we'll see in a second as an example, or we do it right away to get rid of it. And one of the keys I want to really focus on is a little thing called distribution. So let's say we have, let me see if I can remember the problem. I'll probably just make it up. 3 over, oh, 3 times, what am I saying? 3 times 12x plus 10 equals to 12 to 15. Let's start there. Okay. Now I'm making these numbers up, so I kind of may get some fraction answer, but that's fine. But you're gonna see that this one problem has two case scenarios. Student one and student two. These would be our sample points. Two individual students that will approach this one problem in two different ways, yet they will get the final answer correct. And we'll really take a look at why that happens. Why can we do different things but still get the same answer? It's not really the case of doing something different, too. The interesting part is we're technically doing the same thing, but in different orders. So when we deal with solving for a variable, we have to remember we're looking for our goal finale, which we say isolate the variable. Fine. Imagine you are the variable. You want to get to that guy right there in the middle. but there's a bunch of stuff around you. So you gotta meticulously, step by step, start shedding away pieces so you can get closer and closer and closer to X. Moving things away, subtracting, dividing, distributing, whatever steps you decide to take. So student one is going to say, okay, well, that's an obvious distribution. So student one's going to copy this down and say, hey, I know the parenthesis. The 3 goes into 12. The 3 goes into 10. Multiply those, we get 36x plus 30 equals to 15. Cool, fine. That's what student one does. Student two, and I would say is the more clever case scenario. They see a way to simplify this without making their life miserable, because math, right? Again, mathematicians, are we smart? No, we're just super lazy. Do I want to get 36 and 30? Do I want to get big numbers? Not really. Why would I make and force larger numbers to pop out? Student 2 says, wait a second. I can take that 3, and because it's multiplying by the parenthesis, I can get rid of it with the reverse operation. So if 3 is multiplying by the parenthesis, I can divide it by 3, and I can divide both sides by 3. What that means is 3 divided by 3, what does that become? Just a big fat 1. And 1 times anything is the same thing, so we don't even have to worry about that 3 anymore. It's gone. It's basically gone. But 15 divided by 3, 5. So this student now has not changed the values, has kept it as simple as possible. Was it the KISS method? Keep it simple, stupid, or keep it stupid, simple? I don't know. Depends on which side you're on. But the values are much less, so we have smaller numbers to deal with. So what do? We subtract, we follow up, then we have 12x equals to 5 negative 10, or 5 minus 10 is negative 5. And then divide. Yeah, as expected, I got a weird fraction. That's fine. I didn't really plan out the problem, but hey, you're going to notice the next case. So student 2 did not overcomplicate things. They just saw a way to get rid of things right away, removing piece by piece to the other side. Awesome. But what does student 1 do? Well, they got to kind of keep going. They got a subtraction of 30. The 36 is just chilling over there. Then you have 15 minus 30 is a minus or negative 15. Then divide that sucker by 36 on both sides. Opposite operation. So if 36 is multiplying by x, we divide it. Very similar to what student 1 did in the very beginning here. But he did it way up front, and student 1 did it at the end. Notice that difference. Student 1 said, I can divide this out right away. Student 2 said, I can divide it right away. Student 1 said, I'm just going to distribute and keep going because that's the first thing I thought of. And then student 1 has an answer of negative 15 over 36, which, taking a look at these, doesn't look like they are the same. But the question then, is it? So we'll bring out our handy dandy calculator, which we can also simplify, but that's the next step. Just proving a point here. If I do negative 15 divided by 36, that's a negative 0.4167 rounded. So what's the other one? So then we test out the other case. 5 divided by 12. Well, would you look at that? Both answers are actually the same. So student 1 and student 2 arrived at the same exact answer, even though they approached it in two different ways. The key to effectively solving your math problems in class and making the best out of your time is to think, in this case, student 2 was efficient. He didn't, or she, did not make the problem bigger, didn't escalate the values, went for the simplest form, and just got rid of stuff as it started. Student 1 decided that they noticed distribution first, and they went ahead and multiplied the same. So that is the big difference just from the straight beginning. Now, based on experience, student two is going to make less error because they're dealing with smaller numbers. The bigger the numbers get, the more errors students tend to make. So why make things difficult when you can simply shed stuff away piece by piece, right? So based on these two cases, then we see that there are some parallels. Student one subtracted a number, but so did student two. We saw that student one divided the 36, and student two did as well on a different case, but they started off with the 3 up front. But if you think about this for a second, what's 3 times 12? That's 36. They automatically, based on two steps, took that 36 out by dividing it in two parts. First dividing 3, then dividing 12, step at a time without overcomplicating, oversaturating the problem with more heavy numbers. That's the big key. So if you ever see one of your student cadres and they're basically finishing 10, 15 minutes as soon as the test starts, and then everyone else is kind of in the 30 to 45-minute mark, and you're wondering, how did that guy get this test done so quick? They're probably used to doing it and they're familiar with the mathematics in such a way, they're simplifying it themselves all the way through. They're doing less math. They are doing less math. They may have an extra step, but because they're essentially taking a simplification of it, they're just dividing by 3 on both sides instead of multiplying 3 and 12, and then 3 and 10, and then continuing from there. They're taking a very simplified approach by dividing 3 from the beginning. Now we can also simplify the 15 and the 36 by saying, wait a minute, 15 is just 5 times 3, and let's see, 36 is 12 times 3. And then we can cancel those right there. They go to a 1, and we're left with a 5 over 12, or this value. So eventually, here's the kicker. You will do the exact same steps, but they'll be kind of obfuscated in different ways. So that 3 that we identified and we canceled to a 1 is the same 3 that the first student got rid of right away without any hesitation. They just divided it, removed any chances of overcomplicating the problem, and they don't have to think about it anymore. So student 1 did extra steps. They multiplied 3 times 12 and 3 times 10 to make the numbers not only bigger, but they wasted a little extra time just to do that little multiplication versus just getting rid of 3 and calling it a day and then continuing about your process, working with smaller numbers and basically making sure that it's super simplified. So this is the main key, and this is based on to distribute or not to distribute. That is the question. A famous Shakespearean quote. And put a little skull in here because, skull and bones. Distribute or not to distribute. And that's it. That's what you're looking at. Now, it does come in a lot of different formats. You've got the product properties or properties of multiplication, addition, associative, cumulative properties, distributive properties. Those properties are what makes this true and makes both of these answers end up being exactly the same. Your choices in the way you solve a problem will make the problem easy for you or potentially one of the hardest problems you've ever solved. Just based on those choices. There are effective, efficient ways to choose which route to take, for sure. But if we kind of have a bare bones understanding of how math works mechanically, we tend to choose whatever we have at that moment in time. It just comes to our head. Oh, I see this, I'm going to do this, right? The first thing that comes to mind, I'm going to take that path, that direction, which sometimes can be good, can be beneficial. You could find the most effective way, but sometimes or many times you may find just the longest way to get to your final answer. Extra math, bigger numbers, more time trying to do math on the side, all those kind of pieces come to play. So being able to make decisions as you do your problem helps you eliminate complexity, reduce the amount of math you do, or at least the intensity of the numbers you're working with, dividing 36 both sides versus dividing 12, right? And then having to simplify later. And what if you forget this step, the simplification? What if your answer was negative 15 over 36, but one of the questions asked for simplify? This would be minus 2 points because the answer is not simplified. If you didn't get to the 5 divided by 12, that would be the most simplified answer. So, based on the choices, you may have extra work. You may have moments where you kind of stop and you think you're done, but you're not done. But that's all again in the choices we have when we're doing our problems. Everyone can do a problem in many different ways and still get to the same answer. And that's really the gist of it. Make sure you understand your different properties. Then you can make the best choice for yourself and finish 15, 20 minutes. That's it. So that's it. That's all I wanted to go over. I had a student yesterday. They kind of had this problem and they were still getting used to variables. They're not really too fixated on or too familiar with the variables, but we got very good with it. But I did notice this particular problem was very good in showing the choices students can make. Now, if you need personal help, a remote one-to-one session, I do provide tutoring. I provide it from fifth grade all the way to college, university level, and essentially I can help in your university class space if you're a major in computer science. I can't do every single class in university. It's all very specific. So I've helped the students. I've helped over 5,000 students. I've worked at UCF as a math professor assistant and a lab assistant, and basically 500 students in the computer lab, and we're all working on math, and I'm on the board explaining pieces at the whole class, and then I go to the individual students, and they ask me questions on how or what happened and why their problem is wrong. So I've worked with students on basically every single level from basic math, elementary, all the way down to university level. Now, you can find me on Patreon. You can get support on Patreon. I have a free week available for anything from a single hour a month that you can get right now for any math help that you may need. Or if you basically just need, like, hey, I have a picture, here's take a photo of the problem, send it to me, and then I will show you, just like I do right now, the details of how to solve these problems with animation in some form, or at least a little bit of annotation, right? So I do have remote tutoring available for anyone that needs it. I love to stream. I'm always going to be popping in and out of streams and providing little details about what I find my students are struggling with so I can help the overall. Because I noticed that a lot of problems ever since I started tutoring 15 years ago, a lot of problems that students have are universal. A lot of them, sometimes very specific to individuals, but many times, especially when algebra pops up and the variables pop up and all these extra little pieces to understand pop up, a lot of students kind of have the same issues. And I believe it's because the public system has a one size fits all hat when it comes to education. And when you have that perspective to try and fit your method to everybody, it just doesn't get everybody. It might get actually 20% of the students might understand, and the other 80% kind of maybe understand, but even more of them are like lost completely. And the problem is math is cumulative. Everything you know from the past will come to assist you in the future. So having that in mind, always patch up, always understand what you may not know and then go and patch it up with a little research on the side. So like and subscribe. Just know that I do personal tutoring remotely through Zoom, through Discord, all kinds of mediums. You can find me on Patreon/Super Scholar Chris MIA. You'll see the links all over the place. Check my profile as well. But like and subscribe if you like these kind of little tidbits of information. And I will see you in the future.